So here's the velocity time graph for the falling object with air resistance, and it's most definitely not straight. Let's say we want to find the distance travelled between times A and B. To do this, we can split the graph into a series of small time intervals. We'll look at one of these sections and call the area under it delta A, and we'll approximate this real area with a rectangle for now. We can make it look a bit harder by writing it down formally, but it isn't really harder. Here's the velocity at time t, and here is v at time delta t later. That is at time t plus delta t. Delta t is one of our small time intervals that we mentioned above. The area of the rectangle is the height of the rectangle, which is the value of the velocity, multiplied by the width of the rectangle, which is the small time interval. And then we could find a value for the area A under the whole curve by adding the individual rectangles, like this. Here, the summation sign means add together, and we're adding together all the little rectangles from A to B. Will this give us the right answer? Well, in general, no. The rectangles for our graph all slightly underestimate the area due to the shape of the curve. Look at these bits of missing area. But we can get closer to the correct area by choosing smaller intervals of time. See how the rectangles approximate the curve better as we make them narrower. That is, as we shrink delta t. In the limit, as delta t approaches 0, the area of the sum of small rectangles approaches the actual area under the curve. We'll return back to the original picture and write this formally. Here is the sum, written with the limit in place, and an equal sign instead of an approximation sign. When we write this mathematically, we make the following replacements. The limit of the sum becomes the elongated S symbol. The finite time interval delta t becomes an infinitesimal time interval called a differential dt. Then the area under the curve is given by this expression, which is read as the integral of v with respect to t, from t equals a to t equals b. And the process of calculating this integral is called integration. We can regard integration as a process of summation, so that this is true. And all this means is add up all the little rectangles in the limit when they are vanishingly small, so that the rectangles sufficiently well approximate the true curve. So how does writing the maths in this way help us calculate anything? Well, see the block on numerical integration and analytic integration below to find out. What you don't have to do is manually work out the areas of an infinite number of infinitesimally thin rectangles and add them together. Remember, in our example, the area under the curve had a physical meaning, the distance travelled, and there are countless other examples of areas under curves being useful.